higher academic position and has quite a larger research group right now. He's also head of the Peruvian Competence Center of Scientific Computing, which is the German-Peruvian collaboration, and is also the reason why why he is here today and giving this talk probably. His research focuses on adaptive finite elements, flow problems, fluid structure interactions. He's doing many different applications in flow mechanics, especially in medicine, but also, for example, in sea ice simulations and other things. And recently, he's also working in neuronal networks. And I think this is what he's going to talk about today. So I hope Thomas is here and he's able to share his screen. So please go ahead, Thomas. The floor is yours.
Yes, hello. So do you hear me? And do you see me? I hope so. Maybe someone can give a feedback before I start and no one is.
I can hear you.
And do you see my slides?
And yes, that's also fine. Yeah.
Okay.
Yes.
So, yes, thank you very much for this introduction, and also thanks to all the organizers for giving me the possibility to talk a little bit about some very new and recent research that I'm doing in my group with a lot of collaborators. So it is exciting. It would, of course, have been even much better to be in Peru in person, but I guess we all have to wait a little bit longer for this to be possible again. So, yeah, like Stefan said, I'm more coming from traditional finite element analysis and fluid mechanics, but currently one of my projects is also aiming at using the techniques of neural networks to help us in doing finite element simulations. So I do not want to forget what we learned in the last, what I learned in the last 15 years maybe, and what other people have learned in the last 50 years. I think it's not good to push all of this aside. What I want to do is I want to take the best of both of the worlds. So we are trying to identify ways of blending these two approaches, the very classical fluid dynamics approach, using finite elements, finite volumes, it does not matter so much, with some new approaches which come from the area of machine learning. But what I do not want to do in this talk also is to just forget everything about models. So I like partial differential equations, I still want to deal with them. So what I'm presenting you has nothing to do with big data. It's not data-driven simulation. We are still looking at models. So what I'm doing here right now, it's mostly, of course, always a lot of people are contributing, but mostly this is work together with one postdoc of mine, Piotr Minakowski, who is in Magdeburg. Then a friend, Christian Lessig, he's also in Magdeburg, but he's not in the mathematics department, but in computer science. And then a former student of mine, Nils Magenberg. Unfortunately, he left Magdeburg. He's now at the University of Hamburg, but we are still collaborating on this here. Okay. So, this picture, just some circles. But this is in a bit what I want to bring together. We have the models. These models are, for me, partial differential equations. It could be Navier-Stokes equations, but most of this talk, I'm just talking about the Laplace equation, so very simple models. On the other hand, we have this finite element method, which is very well known, and we know how to deal with it. It is very efficient to give us simulation results. And then there's this new world of neural networks, and there's a very tiny piece in the middle of the sketch here. And this is basically what we try to bring together. So how can we combine all of this to get something which is maybe better than what we had before? All of this that I will talk about is really work in progress. We have first results, but this is really active research. Before I really start, I also would like to say one word about what Stefan told you. So we have a nice, in principle, a very nice project in Germany. We called it the Peruvian Competence Center of Scientific Computing. And the idea of this project is we wanted to start, or yeah, we wanted to advance the collaboration that we have with different Peruvian universities and with German universities. And it is a very nice project. We have nice funding to organize summer schools, to organize conferences, to have mutual visits between Germany and Peru. Unfortunately, just after the start, the COVID crisis began, and you all know it. Yeah, it stopped a lot of the plans, and it also stopped a lot of our plans for the time being. But maybe if you want to be informed, just check out the website or write us an email to this mail address that we have. We hope that everything will really come to a start in the next year. Unfortunately, the next year was supposed to be the last year of the project, but we are quite hopeful that we can convince the funders, the German Academic Exchange Service, that everything will be extended for a while. And so I hope that in the future there will be a lot of possibilities again to meet each other, maybe even in person. Okay, but now let's start. So in the beginning, I will mostly give an introduction. So this is nothing that we are doing. This is more something like to get you on the same level that I'm also on now, and to talk a little bit about different approaches of how to use neural networks in the context of partial differential equation. And then the second and third step, I will talk a little bit about our own contributions. So very slow. Please excuse me if this is boring for some of you, because I'm sure that some of you are really experts in neural networks, but I'm sure other people are not experts in neural networks. So before I can tell you how we use neural networks for solving partial differential equation, I talk just a little bit about what a neural network is. So what it can be. So what is it? On the right, you see a neural network. Mathematically speaking, you can say a neural network is able to represent a function. And here in this picture on the right, it is a function mapping from r to the power of 3. So we have 3 input variables, and the output is in r to the power of 2. So we have 2 output variables. So just a function, you have some input variable and the output variable. And the neural network consists in the most simple case of something which we call artificial neuron. This is what you have on the left. So the neural network is a function which is composed of a lot of single neurons. Each of them is built in a very simple way. So each artificial neuron itself, here on the left, is a function which maps from r to the power of n, so entry variables are x1 to xn, to r. So n entries and 1 output variable, and the most simple kind of artificial neuron is just what you see here in this little sketch. It's a linear combination of the input variables with some values wi, we call them the weights, plus another variable in blue here, the b, which we call the bias. So in principle, you can say a neural network or an artificial neuron is nothing but an affine function. So a linear function plus the bias. It looks very simple. Two things happen. This affine mapping is then put into what is called the activation function, and this is sigma. On the next slide, I show you what sigma is. Sigma is also a very simple function, just a scalar function from R mapping to R. So what is a neural network? A neural network consists of a lot of neurons. Each of them is built in the same and very simple way and consists of the affine mapping put into the activation function. And then there are these quantities in blue. What are they? What are the weights and the bias? You can think of the following. The neural network on the weight is the topology of everything. So we put together how the neurons act together with each other, how the output from the one is put to the input of the next, and so on, until we decide we are done, and then we are at the output layer, so the output of our function. But the weights, they make the neural network to act like one specific function. So what does it mean? It means a neural network is something like a function space. It can represent a lot of functions, infinite many different functions, and by choosing the weights wi and the bias values b, we get one specific function. So a neural network is only the topology, and one specific representation asks for somehow setting the right values for the weights and the biases. So a neural network usually has a lot of parameters, and a lot can be 100, 100,000 or 100 million. So there are different application cases, but usually a neural network has a lot of unknown parameters that somehow have to be set. But otherwise, mathematically speaking, we can say a neural network is simply a function mapping from r to the power of n to r to the power of m, depending on how we set up the topology. So last missing thing is the activation function. Usually this activation function is a very simple function, just a scalar function. Usually it is a nonlinear function. And so typical examples are shown here. Maybe the most common use in computer science is called the ReLU function. It is just the maximum of 0 and the input parameter s. It's shown here on the lower right, just this function here. It is 0 on the left, and then it's a linear function on the right. Or the so-called sigmoid function, which you see on the left figure. So it takes the value 0 on the left plane, and it takes the value 1 on the right plane, and in the proximity of 0, it is a smooth transition between 0 and 1. This is where the word activation function comes from. Depending on the input, the result is either 0, so non-active, or 1, active. And this is it. In my world, this is a neural network. Of course, there are much more possibilities and a lot of advanced techniques, but this is all that we need. So a neural network is a function, and it consists of neurons. Each of them is built in exactly the same way, and different functions can be realized by choosing different values for the weights and the biases. So why should it be a good idea to use neural networks to do something? So for instance, to solve or to represent the solution of a partial differential equation. The basic reason is because they have very good approximation properties. So they're rather old results. So these here, my citations that I have here for you, they date back to 1989, but there might be even older functions, and they older citations, and they basically tell the space that is spanned by neural networks is rich enough to approximate every continuous function as good as you want. Or in other words, the space of neural networks is dense in the space of continuous functions. So this has been known for quite a long time, that in principle neural networks can be used to approximate nearly every function that might be of interest to us. And there are a lot of newer results which go to other function spaces. There are also results which tell you how good really the approximation is in a quantitative way. But for us, this should be enough. So these results just show you, in principle, it could be a good idea because we know it is possible to approximate any function which is continuous by a neural network. There's a downside also. These proofs, which are called the universal approximation theorem, they do not tell you how to do it. So it's not constructive. None of these proofs tells you how to design a neural network, how to pick the parameters, so the weights and the bias values, to really approximate a function. All of this is not answered. They just tell you it is in principle possible. Okay, now we go to partial differential equations. There's a big word, it's called physics-inspired neural networks. And this is what I will talk about. And it basically means two things. First thing is, we are trying to represent the solution of the partial differential equation by a neural network, number one. Second thing is, we are using the partial differential equation. This is why it's called physics-inspired. You could also say model-inspired neural networks. The other word would be this data-based simulation, which we are not doing. And PIN, so physics-inspired neural network, is just a big word. There are maybe nowadays 10, 20 different methods. Some of them are seen here on the slide. Maybe the most well-known, the deep Ritz method that I will talk about, or deep XDE, deep DGM. Everyone has its own name, and everything is pretty similar. And this sketch here can show you what is really meant by physics-inspired neural network. You can think of the following way. On the left, you see the neural network, just a sketch. So it's a function, mathematically speaking. Input variables are the space variable x, and maybe, if you have a time-dependent differential equation, the time variable t. Then you have this neural network. It can be as large or small as you want. And then finally, you have one output. This is your function u. And I've shown you before, a neural network consists of two parts. First, it's the topology. We somehow have to design the neural network. And the second part is, to have a single function, we need to know the parameters and the bias values. Now, how do we get them? The idea of these physics-inspired neural networks is the following. You use the neural network to express any solution, which I call u hat. Afterwards, you're computing the time derivative, the spatial derivative, for instance, of the neural network, and then you can use this to evaluate your partial differential equation. So here, just an example, heat equation in one dimension. And then the simplest idea of this physics-inspired neural network would be, we take the neural network, we compute the time derivatives, we evaluate our partial differential equation, and then we use an optimization method and try to satisfy this partial differential equation. So we try to find the missing parameters, the weights and the bias in the neural network, such that the result will satisfy our partial differential equation. This is called the loss function. So it's just the objective function in some optimization scheme. Then we use some minimization method, gradient descent, and finally we get the weights and the bias of our neural network, and we have our solution. This is the idea of it, and I will show you one specific example. I like it most of all of them because I think it's the most simple one and most direct one. We are just looking at Laplace equation, and I guess you know the Laplace equation can also be written as a minimization formulation. So the solution of the Laplace equation is equivalent to the minimization of an energy functional, so the integral over the square of the gradient minus the right-hand side times the function that we want to minimize. And now we have a direct connection between a partial differential equation, a neural network, and our missing minimization problem. What does it mean? We try to solve this minimization problem. So the first step that we have to do is we must fix a function space. So where do we look for our solution u? And here, for the deep Ritz method, the idea is just we take a neural network. We take a neural network, and the solution we call u. But I've shown you a neural network is a complete function space, and a function is realized by picking the weights w and the bias values b. So many, many parameters. Maybe 1,000 parameters are missing, but if we have them, we have a specific function. Okay, and this is it. So the idea of the deep Ritz approach is, instead of maybe using finite elements or a spectral method, we use functions that are represented by a neural network, and the optimization problem now reads, try to find the weights and the bias such that the resulting neural network function is a minimizer over all possible weights and bias values. That's it. So a very, very simple approach, and this is how we can bring together the world of neural networks and the world of partial differential equations. If you look a little bit in the internet, you will find Python scripts, and I think they need about 100 lines of code, and they're really easy to understand, and it is very nice to and fun just to experiment with this. Okay, but we do not want to experiment only, we will also want to know if this is any good. One step is missing. If you've read about neural networks, you will also always have read about, so usually they say you have to train the network. This comes from the language of computer science. In terms of mathematics, you could also say you have to optimize your problem, or other way, you have to minimize your loss function. This is equivalent to training. Okay, but one step is missing. If we want to solve our minimization problem, we always have to compute these integrals. And this is not so easy. So how do you integrate a neural network? So how do you do the antiderivative of a neural network? It's not so very easy because it's a very big function depending on a lot of parameters. It is nonlinear. You always have this activation functions in between. So to get an efficient method, we need to replace this integration by a numerical integration. And in the classical deep-Ritz method, it is done by the most simple integration method, by Monte Carlo integration. So we approximate this integral by picking a number n of random points, this chi I, these are random quadrature points in our domain, and we approximate the integral just by this statistical value here. And then how does it work? We pick a number of random points, let's say 100 points or 1000 points. This we use to evaluate our energy functional, and then we use some optimization method. Usually what is used is called a stochastic gradient descent method, which is a slight modification of the standard gradient descent method. And the reason why it's necessary to do a modification is that we have to deal with such a huge amount of data. What do you mean by huge amount of data? I told you we don't have data. Of course we have data. Here the data are the Monte Carlo integration points on the one hand, and on the other hand, all the parameters of our network. And it can be a lot of them. So we have to solve a minimization problem with maybe 1,000 or 10,000 unknown. So it's quite a large minimization problem that we have to solve. So now a reference which I can really recommend is what I've shown here, called Deep Learning, an Introduction for Applied Mathematicians, because this really casts everything into the language of applied mathematics. So if you know something about gradient descent, it is very easy to read this paper, and it's really a perfect introduction to this topic. So I show you an example. What we did, we're trying to solve the most simple problem there is, the Laplace equation in 2 dimensions. Right-hand side is 1. Homogeneous Dirichlet values, and what you see here on the left is in red the finite element solution, or maybe the real solution, and in blue it is the solution of the neural network. It doesn't look any good, but no problem. This is the solution before we start the training, so before we start the optimization procedure. And now I show you how it looks like after 100 steps of gradient descent. Not very good on the left. It doesn't even have the right sign. 200 steps, 300, and so on. I go on, and you see it's closely approaching something which looks better and better. We are now at 2000 steps of the gradient descent method, and so on. And it gets better and better. It will never get perfect. So it will always oscillate a little bit. Why? Because it's a problem which is too difficult. We are solving a minimization problem with thousands maybe of unknowns. It will be nearly impossible to find the real minimum of this problem. The problem is nonlinear, the problem is non-convex, so who knows if there is a global minimum. We will most likely jump around between different local minima. But as you see, we get a good approximation. On the right, you see the error. The error is getting pretty small. Second example, the same on the L-shaped domain, where we have a singularity in the solution. In the beginning, again, the solution has nothing to do, the network solution has nothing to do with the real solution. And here it goes much faster. Was maybe too fast, yeah, but even so already after maybe 500 steps, the solution looks very close to the real solution. But again, it will always, the network solution will always oscillate around the real solution. So the first thing that we should learn from this is to solve a partial differential equation with neural networks and using the deep Ritz method means we must approximate a very large nonlinear, non-convex optimization problem. Second thing, you will most likely not get a unique solution. You will get something which might be close to a good approximation. But the goals should be a bit different, and they are different from what we expect if we use the finite element method. So here you see approximations to this problem with the finite element method on meshes that get finer and finer and finer. So on the left, just 3 elements, we have no approximation at all. 12 elements, it already looks in principle like it should like. 48 elements, 4 times more, and again 4 times more. So this is how we know usually how numerics work. We increase the effort, so we make the discretization finer and the solution gets better. And remember what you've seen before, it's a little bit different for the neural network approaches. So here on this slide is a lot of comparison between the two approaches. Finite element, and you can equally replace it by finite differences, and neural networks. And I just want to highlight 3 points, these in colors. What does solving mean? For neural network, solving means we are solving an optimization problem. For finite elements, Laplace equation, it means we solve a linear system of equations. So we do Gauss elimination, we do conjugate gradients, or we use a multigrid method. And just guess, what is a simple problem, what is a complex problem? Of course, solving a linear problem is something which we learn very early, maybe at school or at university, and solving non-convex, non-linear optimization problem is something where no one of us really has a good solution. So what does it mean? It means if you look at the complexity of the complete approach, it means using the deep Ritz method is something challenging. It is even challenging for the two-dimensional Laplace equation. And it's not challenging for the finite elements. If you do everything right, if you do the best that you can, which might be something like using a multigrid method, we have algorithms which give you the solution in linear complexity, depending on the size of our solution space. So all of this does not look good. All of this does not look in favor of neural network. But and it is true, as I will also tell you in the next slide, but there's something more. If one gets very close into the proofs of showing how good is the approximation property of neural network, and if one compares it to finite elements, then one sees there is a potential benefit. And the potential benefit is if we look at very high-dimensional problems. If you look at a 10-dimensional problem, for instance, you would see if you do it with finite elements, it would suddenly get very bad, because finite element approximations, here the complexity scales exponentially in the dimension. And for neural network, it seems like the scaling is much better. So there are some applications, for instance, in finance, the Black-Scholes equation, they sometimes have to be solved in very high-dimensional problems, but the Laplace equation is usually 1, 2, 3-dimensional. If we go to Navier-Stokes, usually we look at 2 or 3-dimensional problems. There's nothing like the 6-dimensional Navier-Stokes equation. So there seem to be some cases where this might be having really potential, but really a warning. You should not now start to throw away your traditional simulation techniques and just do it by neural networks. It's not worth it. It's really not worth it because it's much more costly. You're able to solve the Laplace equation with finite elements or finite differences in a fraction of a second, and getting the same quality by something like the Dibritz method will take thousands of operations more, and you will have to wait for a long time. But on the other hand, it is really worth looking at all of this, because I really guess there's a lot of potential and things to be taken. And in the following, I want to just give you a sketch of what I think and what we think that could be done. So of course, one thing is there's something into high-dimensional problems. If you really have to solve a 10-dimensional problems, then you will not get very far with finite elements. So there we need something new. But if you really just have to solve it, 1D, 2D, 3D, heat equation, for instance, it's maybe not such a wise idea to try to use this kind of approaches. At least if you want to get your solution very fast. On the other hand, if you want to learn something about it, it is a very good and also a very interesting thing to look at. Okay, going to the second part. Now something that we've done. So you've seen I'm not maybe the biggest fan of just throwing away our traditional approaches and using neural network. I don't think that it's really the thing to do. But we believe that it's a good thing to mix both approaches. So what do I mean by mixing both approaches? I want to use finite elements or finite difference or finite volumes where we know that they are very good at. So for instance, in fluid dynamics, if you do not need a very high resolution, finite volumes is maybe the best approach that you can use. It has very good conservation properties. It gives you, in a very efficient way, a rough picture of what you expect, how your simulation result should look like. But these approaches have limits. These approaches have limits that have not been solved yet. If you think of fluid dynamics and you want to do a simulation of an airplane that is flying, no one is yet able to really resolve what is happening on the surface between the flow and the airplane. You will have vortices which are so small, but they are very important, but you cannot resolve them. So we cannot do everything with traditional methods. Another example is weather prediction. If we want to do weather or even climate predictions, we need to run simulations on huge areas. In the extreme case, we need to do ocean and atmosphere simulations on the complete Earth. But maybe we're interested in what happens in maybe on the coast of Peru. And then again, we get a problem. With nowadays power, it will not be possible to do a global simulation and having the accuracy to see what is going on in Lima. So traditional methods are not so good in they're not so good in getting the very fine scale of it. In principle, the models are good, they should be able to give us the answer, but the simulation techniques are not powerful enough because it's getting too big. And this is what we want to do. We somehow want to mix the classical simulation techniques with the neural network techniques where the classical do not give us an answer. Okay, but we want to do two things completely different from what you've seen before. The Dibritz method is using a neural network to solve one specific problem. If you change your domain, so if you go from the square to the L-shaped domain, you need to start from the beginning. If you change your right-hand side, you need to start from the beginning. This is not what we want to do. We want to learn the operator. So we want to use neural networks to help us in solving a lot of problems. We want to train a network once, and afterwards we want to use the network to help us solve the Navier-Stokes problem. And if possible, independent on how the domain looks like, independent on how the problem data looks like. And of course, we have not reached all these goals, but this is what we want to do. So I want to sketch our idea really briefly. In classical finite element dynamics, what you have very often is you start with a triangulation of your domain. So this is a slice from a 3D problem, the flow around two plates. You can't see it, but it does not matter so much. This is just a picture of a very, very rough discretization and the numerical solution on it. And then what we do is we refine the triangulation if we want to have a better view, and then more and more features appear. So very often we have a hierarchy of discretizations, starting from a very coarse one, going to finer, finer, and finer ones. And this hierarchy of discretization in the language of finite elements, it gives us a hierarchy of function spaces. So VH1, VH2, and so on. They get finer and finer and finer, or you could say the function space gets richer and richer and richer. And the richer the function space, the better is the solution, but also, of course, the more costly is the solution. And this is the basis of the so-called multigrid method. The multigrid method, in principle, is just a linear solver, and it uses that we can combine the solution on the fine mesh with a coarser, 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 until we reach a very coarse mesh. And this multigrid method, which combine the solution of all these meshes that I've shown you here, and many more if you like, they are able to give you a very good approximation in a very fast time. And this is exactly where we start now. Usually, your finite element level is the finest mesh that you have, and all the coarser mesh levels are used to get your solution in a very efficient way. But now we think this problem a little bit different. The finite element level, here, the blue VHL, is the level of the finest mesh where we do classical finite element analysis, and we use all the coarser meshes to get a solution in a very fast time. But now we assume that there are even finer meshes, HL+1, HL+2, until HN. So we're in the middle of our multigrid hierarchy. We use the coarse meshes for finite elements, and we use the fine meshes now to get an improvement to our solution. But on these fine meshes, we do not want to solve our finite element problems because they get too large. Here we want to use neural networks. So the big difference to what we have seen before is we do not want to solve our equation by neural networks. We want only to get predictions of what we are missing. We want to get predictions of what is going on in the mesh levels that are too fine for us. Just assume you have a weather model and assume you put a finite element mesh on the complete globe, and just assume this mesh has a mesh size of 10 kilometers or maybe 100 kilometers. This is, of course, too small to give you a good prediction of what is going on in a city, for instance. So the idea is, on this 100 kilometer mesh, we are doing our finite element simulation, but then we get the information on the subscales, 50 kilometer, 25 kilometer, whatever. We try to get them from a neural network. So the difference to what we've seen before is, so really the most important difference, this is why I stress this point a little bit. The neural network is again representing our solution, but it's not representing the complete solution of our problem on the complete globe. It is only representing the solution locally. So what you've seen here, this 4x4 elements, you can imagine the following. Altogether, this 4x4 elements, they represent one single element in our finest finite element mesh. We split this into 16 elements, and these 16 elements, here we try to get the solution from the neural network. On the right of it, we have the next finite element mesh. And on this next finite element, on this next element of our mesh, we are doing exactly the same. So we are using one single neural network, and this one single neural network we use in every element of our finite element mesh to get a correction of our solution. So the big difference is the neural network does not know the big picture. It is local. The neural network does not know what is the boundary data. The neural network, if you use it for weather prediction, does not know that next to Lima there's also another city in the world. It only looks locally what is going on here. And this is a great benefit. And the benefit is what is called generalizability. If the neural network doesn't know the big picture, it has the potential to be used in very different settings. It has the potential to be used for different problems. So even if you change your domain, the neural network should still be somehow valid because it does not know the domain anyway. Another advantage is this neural network is small because we are only trying to get a very small prediction. So I can tell you a number for what we are doing here. Small means our neural network consists of 8,600 unknown parameters. So we have to determine 8,600 values for the White functions and the Bias functions. But it is small compared to a network which should give you the complete simulation. Okay, I just show you some results of what we are doing, how something like this looks like. So this comes from a classical fluid dynamics problem. We're solving the Navier-Stokes equation, and we are looking at the flow around a circular obstacle at a moderate Reynolds number. So the flow, here I can show you how it will look like. It develops some vortices behind the obstacle. And what we do now is we train our neural network in this multi-grid approach, and we try to train it in such a way that it gives us very accurate results. What does training mean? Training means one time we have to do a very costly simulation. So one time we do a finite element simulation on a very fine mesh, and we use this to train our, how many were they? 8,600 parameters. So once we solve the optimization problem, then we have it, we store our network, and then we use this network on other problems. So first, we do a very small variation here. We exchange the circular obstacle by an ellipse, and we increase the Reynolds number. And then we are trying to use the neural network to help us get a better solution to this problem. And I just want to show you what it means. This picture is not very interesting. You see three results. Maybe you can't even distinguish them. On the top, you see the result on a finite element mesh. So a lot of effort. On the bottom, you see the result on a very coarse finite element mesh. So I show you the picture here once more. You can assume on the left, so the fine mesh is we are doing really finite element simulation on the final mesh here, which we do not want to use. This turquoise one here. The coarse mesh means we are just doing our classical finite element simulations on the coarse mesh. And now the average, the middle picture means we are using the coarse finite element function and we are improving it with our neural network. And this is not very impressive what you see here, because of course you see some differences. If you look in the wake, our mixed finite element neural network solution, it looks better than just the coarse solution, but it's not so impressive. But if you look at some quantities, it's always difficult to look at solution in terms of just pictures. So what did I show you here? This is now a quantity which is important in fluid dynamics. It's the lift coefficient. The lift coefficient, basically, it is the force that is acting from the fluid onto the obstacle in vertical direction. So the lift is what is making a plane fly. The lift should always point upwards. So it's very important coefficient in aerodynamics. And here the 3 lines that you see. This orange line in the middle is the value of the lift if you just use the coarse finite element solution. The green line is the value of the lift if you do a very resolved simulation. And the blue line, which is very close to the green line, it is the lift of our mixed simulation. So by using the neural network, we are able to improve the very, very fast and efficient finite element simulation on the coarse mesh and make it nearly as good as a simulation on a very fine mesh. And in contrast to the deep RITS method, this does not only work, it is also efficient. So here I have some timings for you. If we do the fine simulation, it takes 500 seconds. If we do the coarse simulation, it takes 200 seconds, but the coarse simulation also gives you very bad results for predicting the lift. If you do the mixed simulation, it takes a little bit longer, so 270 seconds, but at a bit more than half the time, you get nearly the same results. So in principle, you could, I know it is too much, but it's always good to exaggerate also. In principle, you can say you get it for free. So it's not for free, it's 70 seconds, but it's nearly for free. So it saves a lot of time. It looks like it has a lot of potential. I told you this was the very first result. We changed the circle into an ellipse. Now let's make it more difficult. We completely change our setup. Instead of 1 obstacle, we have 2 different obstacles. And we are not doing a new training. So we are just using the neural network that we have saved before, and we are now applying it to this approach. And the results are not as good as before, but please, it is really all very new. So here in orange again is the simulation on the coarse mesh. In green is the fine mesh simulation, and in blue is our corrected simulation. So it's not as impressive as I could show you before, but it gets better. And here, this on the left is the drag coefficient, so the horizontal force. And if you look at the vertical force, then at least you see that the maximum coefficient of the lift is identified nearly perfectly. Okay, again, so I guess I will share the slides afterwards, then you can have a close look at all the references I give you. We have some text on this already. You're also always welcome to just write me an email afterwards. But we believe that this could be a good approach to use neural network really in an efficient way. That really helps us to improve everything. Okay, finally, in some final minutes, I want to talk about the second topic, which I also follow. I'll do it very short, because this is also work in progress. We also have very nice results. There's one criticism. People say, okay, it might work, but everything is just a demonstration. You're just always showing nice examples where everything is working, but you're not able to prove anything. You're not able to give us a guarantee. So can we somehow understand what's going on, and can we somehow do error analysis for neural networks? So can we prove, can we really be certain that what we are doing is not only in this one case giving us a better approximation, but is it maybe always giving us a better approximation? This is what's again called the generalization. So unfortunately, it is really a very, very difficult topic, because if you look at the error between the real solution U and the neural network solution, it depends on so many different properties. It depends on the topology of the network. This is called the approximation error. Then it depends on what kind of quadrature points you have used, for instance. This could be called the generalization error. But then, if you have picked your quadrature points, you still have to solve your minimization problem. I told you it is unlikely that you will be able to solve it. So you have this optimization error. And it is really very complex because there are so many parts contributing to it. And there's very little known. Here's a recent paper which is very nice, which gives some first really analytical theoretical results on it. I'm not part of the list of authors. So what do? We do something more simple. So we want to do the following. We do not want to do a priori error analysis. We try to identify the error of a network that we have. So after training, we try to give a bound on the error of the resulting approximation. And now we are going back to the deep Ritz method. So of course, we start with the most simple one. And if we completely understand this, we will go to our mixed method using finite element and neural networks. So we are using an old idea. An old idea that, so it's not so old, it's maybe 25 years old. It comes from the finite element analysis. It's called a joint-based error estimation or the dual-weighted residual method. So there are a lot of names for it. And one reference that is very nice is this. It's a long article, nearly 100 pages, from Roland Becker and Rolf Ranacher. Okay, the idea is very simple. The idea is we want to have a computable error bound, and this computable error bound should be something which is meaningful. So we want to be able to compute errors in functionals of the solution. So an error functional could, for instance, be the error in a certain point xi. So I pick a point, and the error estimator should tell us what is the difference between the real solution and the numerical solution in this point. And in the language of finite elements, it's a very easy idea, very simple idea. You solve your Laplace equation. Gradient u, gradient test function equals right-hand side. Then you have to do something in addition. You solve an adjoint solution. For the Laplace equation, there's nearly no difference. Usually in the joint, you replace the role of test function and trial function. So you solve the adjoint solution z. It's also a Laplace equation. And on the right-hand side of this adjoint solution is our error functional. And then you have something which is an identity, which you can use to express the error. Very simple. It's just a residual evaluation. You have to compute the integral of the right-hand side and the adjoint solution, and you have to evaluate your variational Laplace operator. And this idea can be transferred to neural network solutions without even thinking. Because what is a neural network solution? I told you a neural network spans a function space. It's a difficult function space. It's not a linear space, but it's a function space. And if you pick weights and Bias functions, you get a function. And if you take care that your activation function is differentiable, then it's also rather obvious that the space of neural network functions is a space of differentiable function, and it's a subspace, if you do it right, of the Sobolev space H10, so of our finite element space. And that's it. If we want to use the idea of error estimation for neural networks, we can just do the following. We use our deep Ritz method to get an approximation to this minimization problem. So that's the same that we had before. We are minimizing the energy functional. So we try to identify the optimal weights and the optimal Bias function. And then, because it's just this quadratic minimization problem, we see that this is equivalent to solving a variational problem, so the Laplace equation just written in the language of neural networks. It's just good to see that it's equivalent. We are not using it. We are minimizing the energy form, but of course it's equivalent. And then finally, we can plug in this discrete function into our error estimator. So instead of having the discrete function UH coming from finite elements, we just plug in our neural network function. There's one missing link. And this would require a complete talk. We need an approximation of the adjoint problem. And what we do here is we just solve it by finite elements. So it looks like we are turning ourselves in circles here, because I want to avoid finite elements, but now we are using finite elements. But it turns out that it's really not a big problem. So we need an approximation of the adjoint solution, and we do it by finite elements, but we do it by a very coarse finite element function, which has maybe 50 elements or 100 elements. So we need to solve a tiny linear system of equation. So it is for free, and here are some results. It's the second example. We are solving Laplace equation on the L-shaped domain. We are trying to estimate, so we're trying to validate that the error in this point here on the lower right is exact. And what I show you in this table is during the training of the neural network, so after 500 iterations, 1000, 1500, and 2000 iterations, I show you what is the real error of our solution. So u minus uh, I can here compute the real error because this problem is so easy. Then what is given by our estimator, and this effectivity is just how close is the error estimator to the real error. One would be perfect, and what we are doing here is nearly perfect. So what does it mean? It means if you train your neural network, and this is what you see here, so you do a couple of thousands iterations of the gradient descent method, you can use this error estimator to tell you how good are you. Because we need something like this to decide when are we done. And this is what we have. Look at the middle picture. We're solving the adjoint problem on a finite element mesh with 48 elements. So we are solving a linear system with 48 times 48 entries. I think this is done in a millisecond. And this can then be used, so we only do it once, and this can then be used during training to estimate what is the error, and we can use it for stopping criteria. It is really simple, all of this, but it is a, I guess, first very important step that we cannot only show in terms of picture that it's working, but that we can also get bounds of the error that really seem to be very accurate. So this was just an overview of some of our approaches that we are now really working on intensely. I hope there will be more coming very soon, but we already have quite a large number of first results. And if you're interested, ask questions now or just write me an email. Thank you very much for your attention.
Okay, thank you very much, Thomas, for this very interesting talk, in my opinion. So I think we have some time for questions. So you could just write to the chat if you have any question, or maybe raise your hand. Okay, maybe everyone wants to have lunch.
Yeah, which I can completely understand. But really, if you if there will be questions, you're always invited to just write me an email.
Okay, otherwise I maybe have one question. If you go to slide 21, you explained that this neural network can be seen somehow as a correction on the finest mesh. So another alternative to get such a correction could be to solve a local problem with finite elements, like in a domain decomposition way. So what is the advantage of using artificial neural networks here?
So I think it's really comparable. But I think the advantage could be that we don't have to solve. So the thing is, training a neural network is a big job. So it takes a lot of time, and it's not really known how to do it in an optimal way. But we train the network only one time, and then we have it, and afterwards applying the network just means doing some matrix vector multiplications. So this could be the advantage, that if you have a network which is trained, it is more efficient to just use it. But on the other hand, I completely agree, it is very similar, and it should be tested. This is what I mean. So of course, all of this is very interesting to just try out, but it should be tested if it's really more efficient. But I believe it really has the potential to be more efficient, because they really have very good approximation properties, and once trained, they are immensely fast.
Okay, thanks. So I do not see any questions. I hope that I'm not missing something. Yeah, now I see that.
Yep.
I think there's one question in the chat. What software do you recommend to use neural networks for PDE?
So I am always using PyTorch, because I think it is very easy to use. And for me, it was so fast to get into it. So PyTorch is a library for Python, which for small experiments, it's perfect to use. And for us, it has another benefit, because it is pretty simple to do some first experiments using neural networks, but it is much more difficult to use to do some experiments using finite elements. So our finite element software is in C++, and this PyTorch can be used in C++ very easy. So I really recommend it. It is perfect for starting, but it also has the potential to be used together with other programs. Then there's a second question, but Stefan, I hope you can translate it. My Spanish is not so advanced.
Okay, let me read it in Spanish first. Dentro de este esquema se puede trabajar con razonamiento basado en casos. I don't know, tal vez alguien puede traducir la pregunta a inglés.
So I quickly answer the next question. If it's necessary to use TPU acceleration, no, it's not necessary. So we have not used it yet. We use it for training, because training takes rather a time, but we have not used it for applying it afterwards. Our networks here are so small that it's not necessary. It gets necessary if the networks are really big, so if you increase at least 1 0 to the number of parameters, then it really helps. This is a good question. I have to tell you that I do not really know. I think I so I think that I that I don't even know. I have to admit what it is. So I have no experience with this. Unfortunately, I cannot give an answer to this case-based thinking. Yeah, sorry, I don't have any experience with this, so I don't know.
Okay, are there any further questions? Otherwise, maybe just contact Thomas by email. And okay, then yeah, let's maybe thank Thomas again for this talk. And I think there's now a break for you to have lunch, and probably after lunch it will continue. No sé si alguien de los organizadores quiere decir algo.
So,
Sí,
muchas gracias.
bueno, gracias, Rachel, Tomás, por tu presentación. Los invitamos en la tarde a las 2:30, empiezan con el curso 2 en la sala 1 y también con la continuación del workshop de optimización en la sala 2. Así es que tenemos un tiempo de almuerzo y volvemos a las 2:30. Gracias.